Hi, my name is Sean Everett, and today I'm going to talk about the semester project we did for Business Intelligence Tools and Technologies for the spring semester 2019. The name that we gave our project is a data mining approach to predict patient length of stay at hospitals. We utilized the CRISP-DM approach to build our model, and I'm going to talk about the business understanding of our project, the data understanding, the data preparation, and then my counterpart will talk about the modeling and evaluation of the model. Patient length of stay, which is our target variable for our model, is one of the most important metrics in healthcare analytics. It can be described as the duration of inpatient days calculated by subtracting day of admission from the day the patient is discharged from the hospital. According to the Agency for Healthcare Research and Quality, the average cost of inpatient stay is $10,400 per day for each patient. In total, inpatient visits cost the U.S. healthcare system more than $377 billion each year. There's several reasons why LOS is an important factor. The first is higher LOS can result in longer patient waiting queues and prolonged admission scheduling, which can potentially lead to higher mortality rates. Second, extended LOS can increase the risk of healthcare-acquired infections amongst patients. Third, discharging a patient before they're fully recovered can increase the risk of readmission as well. So overall, predicting LOS can help ensure proper allocation of resources. The objective of our project is to build a predictive model to predict LOS, patient LOS, using data mining techniques and to identify the best model for predicting LOS from several different regression models. Data understanding. For our project, we had to use the Cerner Health Data Set, which is a 2-week snapshot of data, and the tables that were included within that data set were encounter, medication, diagnosis, lab procedure, clinical event, and procedure. Now, the encounter data set includes variables such as patient age, race, hospital beds, patient discharge, and admitted dates for 107,810 encounters. Those are unique encounters. The medication data set contains information regarding the medication prescribed to the patient for each encounter. The diagnosis data set contains information for the physician's patient diagnosis for each encounter. The lab procedure data set contains information on lab tests, information such as hemoglobin and CBC tests. The procedure data set contains information for procedures performed during the encounter, such as antibiotic injections, cardiovascular stress tests, and surgeries performed. Finally, the clinical event data set contains information such as patient's blood pressure, heartbeat, and pain scale rating. The next slide in our presentation is data preparation. As you can see below, we've provided a snapshot from our KNIME workflow showing all the nodes that we used in our data preparation phase of our model building process. So for our project, in order to predict LOS, we decided to relegate our scope to the diagnosis and encounter tables only. We interjoined them using a joiner node, joining by the encounter ID, which is the primary key. Next, in order to create the LOS target variable, we had to convert the admitted and discharge date fields to datetime formats because they were strings. So we used the string to datetime node to convert them, and then afterwards, in order to calculate the length of the stay target variable. In days, we use the date and time difference node. Next, we use rule-based row filters and rule engines to limit and consolidate our data set and our variables, which I'll talk about here next in the presentation. The first rule-based row filter that we used was applied against the gender variable. We had several unknown categories. We had null, unknown, invalid, and not mapped. And according to the bar chart here, it was less than 100 records for each one of those categories. So we decided to remove them from our data set using this rule-based row filter. Rule-based row filter number 2. We used another rule-based row filter to limit our data set to discharge to home records only. There's a variable within our data set called the discharge code description, and it indicates the different discharged categories. And as you can see in the bar chart, discharge to home had by far the highest count at 82,488 rows, and the next highest was null at roughly 20,000 and something. And we decided to remove null because we don't know, it's ambiguous what happened to the patient, whether they were discharged to home or whether they expired. We really don't know, so that's why we felt the need to exclude null records from the data set. And then all the other ones, there's about more than a dozen. They had pretty low row counts, so we decided to remove them as well. Rule-based row filter number 3. We used a third rule-based row filter to exclude records from our data set that had a negative LOS value. That is, the length of stay was less than 0, which is illogical because a patient can't be discharged before they're admitted, so obviously those dates had to be errors. So that's why we removed those records from our data set. On to the rule engines. Now we used rule engines to reduce the categories / groupings for several of our variables to simplify our data set as much as we can for plugging into our model later on. So the first rule engine was applied against race. We have about 10 different race categories: Caucasian, Hispanic, African American, etc. And 3 of them are basically unknown categories, so we grouped them into an aggregated category called unknown. So unknown, not mapped, and null went into the unknown category. And then Pacific and Eastern were relatively underrepresented, like there's not a lot of records with those races, so we grouped them into the other category. And then we grouped biracial and African American, and that's it. Rule engine number 2. The second rule engine we used was applied against the pair code / insurance variable. It's the variable basically conveys the type of insurance or payment the customer used for their encounter visit. We had 15 different categories, and we aggregated them. We pared them down to 6 categories. So the main change that we applied was we grouped the different private insurance types into one category called private, and then there was several different government type of insurances that we grouped into government, and there were a couple of unknown, not mapped, missing that we grouped into unknown. Rule engine number 3 We use the third rule engine to reduce the categories in our marital status variable. We start out with about 9 different categories, and we use the rule engine to pare it down to 5 categories. So the biggest change here is that we group the unknown not mapped and null into a unknown parent category, and then we grouped legally separated and divorced together into their own parent category. Rule engine number 4. Now this is the last rule engine that we use in our data set, and we apply it against the diagnosis description variable, because there were 5,242 unique diagnosis descriptions for our diagnosis variable, which is a lot. So we did some digging, and we realized that these diagnosis descriptions are based on the ICD-9 information, so they can be grouped to at least 7 different categories. So we reduced them down from 5,242 to just 17 categories. One of the problems that we ran into after combining the encounter and diagnosis tables is that it created a duplicate encounter records, because there's a one-to-many relationship between the encounter and diagnosis tables. That is, there's one or more diagnosis records for each encounter record, and we really want a one-to-one encounter to diagnosis ratio whenever we plug this data into our model. Thus, we use a one-to-many node to convert the newly created diagnosis category variable into 17 new columns, one column for each diagnosis grouping. And the one-to-many node populates a 1 or a 0 to indicate yes or no for each type of diagnosis for each encounter record. So after that, we use a group by node to basically summarize those counts, those diagnosis counts for each type of diagnosis, and we create a unique record, a one-to-one ratio for each diagnosis and encounter record. The final node that we applied against our data set for the data preparation phase was the numeric outlier node. When we initially built the models without the numeric outlier node and ran them, the adjusted R square scores were relatively poor for the decision tree and linear regression. It was 0.33 for the linear regression and negative 0.1 for the decision tree, and we wanted to try to improve that. And when we visualized the LOS, we had an inkling that it might be impacting the model performance, so we decided to implement this numeric outlier node, and we went through several iterations of tinkering with the interquartile range multiplier until we got to a point where it improved our regression model scores while also keeping as many records as we possibly could. So ultimately, we applied a 9.0 interquartile range multiplier, and we removed 547 out of 46,299 records. This is basically a snapshot of what our final data set looks like, the data set that we plug into our models. We have 28 variables, 17 variables. 17 of those variables are then the diagnosis variables that we created, and we have 45,750 records to input into our model. After the data preparation phase, we did several nodes on the visualization just to get an idea of what variables might have an impact on our model performance. And the first one we looked at is gender. So we calculated the mean LOS, length of stay for gender, and as you can see from the bar chart, the LOS is pretty close between male and female, so gender probably isn't going to have much of an impact on our model performance. Next, we're looking at the mean LOS for race. In the bar chart, you can see that the Asian race category has the highest mean LOS of almost 8 days, while the category with the lowest mean LOS is the parent category that we created, other, which includes Pacific Eastern race types. The next visualization that we did was the mean LOS for marital status. And looking at the bar chart depicted here, it appears that married patients have the highest mean LOS at about 5.5, 5.7 days, while single patients have the lowest LOS at about 3 to 3.5 days. This next slide depicts our visualization for the mean LOS for our variable patient status. Patient status indicates whether it was emergency, inpatient, laboratory, outpatient, etc. And looking at the bar chart, it appears the recurring and series patient types have the highest mean LOS. So those values could have a significant impact on our models. Our next slide concerns the mean LOS for our payer code / insurance type variable. It appears that the government insurance type has the highest mean LOS at about 7.8 days, while the self-pay payer code type has the lowest mean LOS at 2.5 days. And that's an interesting insight because self-pay patients are most likely patients who don't have insurance. Thus, perhaps this means that those patients are being prematurely discharged on average. Our next slide covers the mean LOS by admission type variable. Now, the different admission types are like elective, emergency, newborn, trauma center, urgent, and it looks like the elective category has the highest mean LOS at 7.18 days, while emergency patients have the shortest LOS at 0.5 days. Next, we created a scatter plot for the mean length of stay by age for the patients in our data set. And you can see from 12 to 16 years of age to 62 to 64 years of age, there's an upward trend. But then after 64 years of age, there's a downward trend up until 94 years of age, which is definitely interesting.
Hello, my name is Sheikh Shahed Uddin, and I'll be talking about the model building approach and model evaluation approaches. So for the model buildings of our project, we adopted regression modeling technique that basically projects the dependence of a response variable based on a set of one or more input explanatory variables. The way regression modeling works is they develop a number of additive mathematical relationships based on some mathematical equations that can forecast the response variable based on a given set of input explanatory variables. There are two ways to determine the accuracy of regression models. One would be the root mean square error, or RMSE value, and the R-square value. The root mean square error value basically projects the differences between the predicted value of the response variable and the actual value from the observation. So it can be assumed that the lower the RMSE value, the higher the accuracy of the regression model. In terms of R-square value, it could range from -1 to +1, whereas a -1 value reflects that there is a negative relationship between the response variable and the input variables, whereas a positive value would reflect that there is a positive relationship between the response variable and the input variables. So the way we can determine the accuracy of our model is a best model would have a lowest value of RMSE and a highest value of RS squared. And for the model buildings of our projects, we came up with 4 different regression models. They are random forest regression, linear regression, decision tree regression, and graded boosted regression. For the model building approach, we adopted stratified sampling with tenfold cross-validation methodology. Doing so allowed us to split the dataset into 10 equally and mutually exclusive datasets, and sampling was conducted from each of these subpopulations. This is done to improve the overall accuracy. And the final accuracy was conducted based on the average accuracy from all of the sampling from the 10 equally divided datasets. And then we have the regression squares, which is the result of the sum of regression squares divided by the sum of total squares, and the final value would be deducted from 1. Here is a layout for the decision tree and random forest regression model that we developed. As you can see, there are learner nodes and prediction nodes for each of these models that was derived from the cross-partitioner node, and eventually the output from the prediction nodes were fed into the cross-aggregator node, which eventually resulted the visualization nodes for line plots and numeric scorers. One important insight that we received from the random forest regression node is the attribute statistics table. From the attribute statistics table, what we see is that the number of time a variable was selected for the number of splits, and this gives a rough estimation about the important role that a variable plays for predictive model building. As you can see at the table, the top 5 variables that were selected for initial splitting were race, pair code description, patient type description, admission type code, and bed size range. And one interesting thing is that age in years wasn't considered as an important variable for initial splittings. While this might not be a very precise estimation for variable of importance, but still it gives us an important significance or important insights. So this is a part of the decision tree regression model that we developed for one of our model building. So decision tree regression model is a type of model where the dataset is broken into a smaller subset that follows the form of a tree structure. And the topmost node is called the root node, and the decision nodes follows 2 or more branches. So one important insight that we got from the decision tree prediction model is that we can, similar to the random forest regression model, we can also look at some of the important variable for some of the initial splitting. So if we look into this initial splittings, we can look that some of the important variables are patient type description and different types of diagnosis, say for example pregnancy, or inpatient or outpatient surgery type. And also bed size range also came up as another important variable in the initial splittings of the decision tree regression model. Here are the 2 other regression models that we built for our prediction model purposes. One is linear regression and the other one is gradient boosted trees. In the next slide, we talk about some of the variables of significance from the linear regression learner node. And for the gradient boosted trees, we didn't have much of the results to be discussed. So the next slide, we talk about the variables of significance. So the linear regression learner node provided us with some significant statistics on variables of significance. So for that, we targeted our confidence level at 95%, and based on that confidence level, we came up with several variables of significance. One important insight from this table is so this table came with not the variable as a whole, but it breaks down into individual groups, down to the individual groups. Take for example, if we look at the very first variable, which is patient type description is equal to recurring, we can see that the significance level is very high, which is close to zero. So this is a very highly significant variable for model building. And then the coefficient says it's a positive value of 25.457. So we can tell that LOS and recurring patient types are positively correlated with each other, and that tells us that the LOS regression slope increases by 25 days when the patient type is recurring. So that's pretty significant information that we can derive from this table. Another important insight can be developed as if the patient has a blood-related diagnosis, the LOS regression slope increases by 0.663. So that's a positive relation again against in between LOS and blood-related patients. And the p-values in this for this variable is also highly significant, which is very close to zero. So this is the important part of our project report, where we discuss, where we evaluate the different models and their accuracies. So if we look at the table, we can see that the R-square values of each of these models are more than 0.8. So that tells us that all the models are sufficiently reliable based on these values that are greater than 0.8. If we look at the mean absolute error value, or MAE values, we can see that the values range from 1.2 to 1.5, which pretty much excuse me, which pretty much tells us that the difference between the mean predicted outcome and the actual outcome are off by an average of 1 day. And looking at the RMSE values, those are not much as well. They range from 3 to 4 days almost. So that gives us a pretty much good idea that the RMSE values are not that much actually. So talking about which is the best model, so like we said in the previous slides, that will select a base model based on the highest R-square value and lowest RMSE value. So if you look at the table, we can see that the random forest regression model gets the highest value for R-square, which is 0.909, following by decision tree regression model, which is not the decision tree model, but the linear regression model, which is 0.887. And also for the RMSE values, again, the random forest regression model came up with the lowest RMSE value of 2.955, following the linear regression model with 3.309. So we can decide that our best model for predicting the LOS would be random forest regression model. Now that we have decided which is our best prediction model, which is random forest regression model, let's talk about the prediction evaluation of these models for some of the variable types. If we look at the admission type line chart, we can see that the prediction model almost accurately predicted the mean LOS for elective, emergency, newborn, and urgent admitted patient types. If we look at the trauma center patient types, the predicted LOS is deviated by an average of 1 day from the actual mean LOS. Looking at the patient type line chart, we can see that the accurately predicted variables are emergency, inpatient, recurring, series, and outpatient, and also short stay patient types. So those patient types are correctly predicted by the prediction model. However, for the pre-admit patients, the predicted LOS deviated by 5 days from the mean LOS, and for the laboratory patients, the predicted LOS deviated by 1.5 days from the actual LOS. Looking at the pair code description type line chart, it appears that the prediction model almost accurately predicted the grouping variables, and there isn't actually any significant deviation from the actual mean LOS for the predicted LOS mean. Looking at the marital status line chart, it also appears that the model almost accurately predicted the mean LOS, and there is not any significant deviation from the mean LOS with the prediction LOS. Looking at the age in years line plot, we can see that the ages against the LOS are pretty much scattered, and there is an increasing trend in LOS from the age of 18 or 20 until 64, and after which it drastically fell down. So interesting part is that throughout this entire time frame, our prediction model almost accurately predicted the LOS, and there isn't any significant deviation from the prediction LOS with the actual LOS. Looking at the ethnicity line plot, we can see that for patients from Asian background, the predicted LOS deviated by an average of 1 day from the mean LOS, and other than that, the rest of the race groups almost came as accurate as the actual mean LOS. Based on our report, we came up with some limitations for our prediction model. The first one could be that our Asian patients came up with the prediction LOS that was off by a day from the actual LOS, and the other one could be the pre-admit patient types that came up with the prediction LOS that were 5 days off from the actual LOS. So those two were the potential footholds for our projects, and based on that, the recommendation could be that maybe we might eliminate the race variable altogether from the modeling, and also maybe consolidating the admission types might improve the prediction model. To conclude our project, random forest regression was the best model determined, and some of the significant variables for developing the prediction models came out as patient type, admission type, hospital bed size ranges, patient age, and certain patient diagnosis types. And also, further improvements are needed before applying the predictive model into real world problems. With that said, thank you for listening to our presentation.